In this video, we will look at classifying chemical reactions into 5 types and using the patterns that emerge from the classification system to predict products of chemical reactions given their reactants. So whenever we look at a chemical reaction, and if we look at the structure of it, as we've said before, we have reactants, and those reactants react with one another and yield products. We're going to focus on this side and look at patterns that result from how reactants combine with one another, and we can use those patterns to predict the products of the chemical change. The only way to truly know what the products are is to analyze the products chemically, but we can use several, there are more than rules of thumb, but there are several patterns, as I said, that emerge from studying chemical reactions that tend to, in most cases, predict actual products. So when we look at the reactants, we're going to have a combination of compounds, elements, and all sorts of combinations of them. And we're going to look at how, what we see here in the reactant side, and that will tell us what the products are going to likely be. Our first type of chemical reaction is going to be the single replacement, also sometimes called single displacement. The general pattern of this is going to be that we're going to have an element plus a compound yields another element plus another compound. So if we use some sort of generic symbols, we can say element A reacts with compound BC to yield, make it element, B plus AC. The other option is that we could have X plus YZ yields Z plus YX. And the difference between these two is which element is being replaced. In this case, we would have A replacing B. B is removed from the compound and A takes its place with C. This is a metal, or we'll just say positively charged element replaces a metal or another positively charged element. In this case, X is replacing Z. This is going to be a nonmetal replaces nonmetal. Okay, and in this case, we can see that it's the nonmetal. This in our compound here, this would be our positively charged element. This would be our negative. So our element X is going to replace the negatively charged element, implying that it itself is also going to be negatively charged at the end of all this. And A reacts with BC. B is the positively charged oxidation state, whereas C is our negative. A is replacing B, so that means A must have the ability to develop a positive oxidation state, meaning that it is likely metallic, and a negative there, C remains negative. Elements that are in their pure state, such as A or X, have 0 for their oxidation state. So we have A going from 0 to a positive state. That's something that a metal would do. X is going to go from 0 to a negative state, which is something that in general a non-metal would do. So these are the patterns that we're going to look for. So we're going to start with the metal-metal replacement. Okay, and that is the A plus BC yields AC plus B arrangement. Okay, and our first example of this is going to be potassium with sodium chloride. So we've got potassium reacting with sodium chloride. Okay, we have over here an activity series. An activity series tells you which element is more reactive than which element. Okay, in this case, if potassium is more reactive than sodium, then that means it has the potential to take its place. If, on the other hand, sodium is more reactive, potassium cannot take its place. So we have to know, is potassium more reactive than sodium? We consult our activity series. You can see the potassium's here and sodium is here. In general, the higher up in the activity series, so as we go up the series, most reactive. So an element high in the series can replace any element lower in the series. Potassium then does have the ability to replace sodium. So what's going to happen is that potassium takes the place of sodium to yield potassium chloride. Potassium takes its place, and then sodium is removed. Now, this reaction may not actually happen, but this is at least the pattern. Okay. Now, we also want to check our balancing, and if you inspect this closely, you'll see that the reaction is completely balanced as written. Let's try another. We've got zinc reacting with copper 2 sulfate. Of course, being able to write chemical formulas is important. This reaction would happen, and I'm going to add some state symbols to this. Solid zinc reacts with aqueous copper 2 sulfate. So this would be solid zinc metal dropped into a solution, blue solution of copper 2 sulfate. Okay, we need to see, is zinc more reactive than copper? And we come down here, we find zinc. Zinc is here. Copper is way down here at the bottom. Zinc is well above copper in the activity series. So zinc is going to replace copper to make zinc sulfate. I'm using the oxidation states for, as I write the formulas for this, zinc is positive 2, sulfate's a negative 2, and then copper is removed from solution. And again, this is a balanced equation. This copper would be solid metallic copper, and the zinc sulfate is soluble and aqueous. So aqueous, remember, means dissolved in water. Make sure of that. Solid and dissolved in water is what the AQ means. Okay. Silver reacts with magnesium chloride. So we're going to compare our two metals. We've got silver here, and we've got magnesium way up here. The question would be, can silver replace magnesium? Remember, any element higher in the activity series has the ability to replace an element lower in the activity series. So in this case, magnesium is higher. Silver cannot replace magnesium. So this solid silver in an aqueous magnesium chloride, and what that's going to produce is no reaction. Silver cannot replace magnesium. The reason for that is that we would say magnesium is more reactive. Now, what does more reactive mean? For a metal, we would say a metal is more reactive if it's easier to remove electrons. So that would be, for instance, a low ionization energy. and a larger radius. Those would be two things that we could put in. There may be other ways of looking at it as well. And we could look at, for instance, electronegativity probably and make some sort of decision, but ionization energy is probably the best one to look at. Magnesium, in this case, has lower ionization energy. So it tends to not hold on to its electrons very well, which means it has low attraction for electrons. Silver, on the other hand, is the opposite of this. It has a higher ionization energy, which means that it's harder to remove electrons. Now, where are these electrons and where are they going? Well, the electrons, if we go back a slide and we look at zinc, which has a 0 charge, with copper 2 sulfate, this is a positive 2 charge, and that produces zinc sulfate, where zinc is now a positive 2, plus metallic copper, the 0, we've had some electrons transferred. Our copper has gone from positive 2 to 0. So this is a reduction of charge. That means it's gained electrons. Our zinc, on the other hand, has lost electrons. We say that it is oxidized. Okay, so if we have a reduction of electrons and attraction for electrons, that means that copper is a stronger attractor of electrons than zinc is. Zinc's not holding on to its electrons as easily, so it loses them. Copper takes them. So if we look at the magnesium and the silver, silver has a strong attraction for its electrons. Magnesium has a low attraction for electrons, relatively speaking, so the magnesium is not going to accept electrons from the silver. There's no tendency to oxidize or reduce between these two particular elements. Therefore, no reaction. Now, let's try another. This is a single replacement where we have an active metal with water. Okay, an active metal is going to be a metal that can replace hydrogen from water. So let's just take a look at this first. We've got magnesium plus water, Mg plus H2O. Okay, we look at the activity series, and there's some other things added out here. So, for instance, the elements in this group, from lithium down through sodium, can replace hydrogen from cold water. In this case, from magnesium to cadmium, we would say that they can replace hydrogen from steam. So, I've now added gas here to imply that we have steam and magnesium. So in this case, this says that magnesium can replace hydrogen from steam. The pattern that gives is, if you think of water as, think about the Lewis structure for water. We've got this structure with two lone pairs. We're going to replace the hydrogen. So a hydrogen comes off, and that leaves, that's a hydrogen with a positive charge, that leaves an OH, I'll make that an H, with an extra electron pair, and that means that we've got a negatively charged hydroxide out here. So the pattern that this is going to be produced is going to be magnesium combining with the hydroxide, so it's a -1 charge. So that gives OH2, plus, this is happening twice to give two OHs, so that's going to give H2. Okay, so we've got H2 and OH2, that's going to be 2 of these plus 2 of these. That means we had to have 2 of these to begin with. So that means we're going to have magnesium plus 2 waters yields magnesium hydroxide plus hydrogen gas. This is gas. Remember that hydrogen is one of our diatomics, and this is going to be dissolved in water, so this would be aqueous. Okay. So balanced, we would have to have the 2 in front of the water. Okay. Let's try copper plus water. So we've got liquid water in this case, or steam, it doesn't matter. And copper, we're going to have a solid. Okay. We look through our activity series, and we find that copper is in the group that includes this long arrow. This long arrow says it can react with oxygen to form oxides. The only ones that can react with water, cold water, would be the first group. React with steam to replace hydrogen would be the first 2 groups, but copper's way down here. Copper cannot replace hydrogen from water. If you think about it, if that was the case, there would be a lot of fountains with a lot of hydrogen gas being produced as people throw pennies in fountains, and that doesn't happen. So we would have no reaction in this case. Okay. Let's try sodium with water. Solid sodium plus H2O, liquid. We'll make this cold water. Okay, we look to see, can sodium replace hydrogen? So we've got sodium is right here. It is in the first group of elements that can replace hydrogen from cold water. So the pattern is going to be sodium hydroxide replaces the hydrogen, leaves hydroxide, plus H2, hydrogen gas. That means we're going to have a 2 here. Okay, a 2 here and a 2 here. 2 sodium, 2 sodium. 4 hydrogens. 2 plus 2 would be 4 hydrogens, and 2 oxygens. 2 times O is 2 oxygens. Okay, and this is aqueous, and this is going to be a gas. Okay, so our last 3 have been metal with water. This is still an element plus a compound. So it still fits the pattern of single replacement. Okay, let's try metal-acid reactions. In this case, we're going to have a metal, which is an element, such as zinc, plus hydrochloric acid, which is a compound. So, still single replacement. So we have Zn, solid, plus aqueous HCl. I'm adding the state symbols. I'm not necessarily expecting you to, but I would like you to be able to interpret what they're saying. HCl is an acid, zinc. Okay, let's find zinc in the activity series. It's right here. Okay, all elements through lead, through right here, can replace hydrogen from acids. So zinc is included in that. So zinc can replace hydrogen from acids. So that means zinc is going to combine with chlorine, and that's going to produce hydrogen gas. Keep in mind that zinc is a positive 2, chlorine is a negative 1, so it's going to be ZnCl2. We have 2 chlorines and 2 hydrogens, so we need a 2 in front of HCl to give a balanced equation. This would be aqueous, and this would be a gas. Calcium with hydroiodic. Calcium, solid piece of calcium plus hydroiodic acid, a binary acid. All of our acids are aqueous. And we're looking for calcium. Calcium's way up high here. It can replace hydrogen from cold water. It can definitely replace hydrogen from acids. So this is going to be calcium iodide, CaI2, plus hydrogen gas. This would be aqueous. Okay, and then we have copper plus sulfuric acid. Sulfuric acid is hydrogen with sulfate, H2SO4. Aqueous sulfuric acid, solid copper. We come to our activity series with single replacements. We find copper down here, Lead is where it ends for replacing hydrogen from acids. Copper cannot replace hydrogen from an acid, so we end up with, excuse me, I'm writing the equation as if it does happen, no reaction. All right, and our last type of single replacement reaction is the halide-halide. This refers to halogens. Okay, so in this case we've got sodium iodide, which is a compound, plus bromine, which is an element. So we've got element and compound reacting. That's the telltale sign that we have a single replacement reaction. So NaI plus Br. Bromine, all of the halogens when they're in their pure state are Br2. So here we're going to have the halogen replace the halogen. Okay, this would be aqueous, and this would be maybe liquid bromine. Okay, so our activity series for halogens follows the same pattern. The higher it is in the series, the more reactive it is. In this case, we're trying to see, is bromine more reactive than iodine? Bromine is higher than iodine, so bromine can replace iodine to give NaBr, which is aqueous, plus I2. All halogens in their natural state, in their free state, are diatomic. So this would be a solid, and it actually would, the majority of it would float on top of the aqueous sodium bromide solution. Okay, try another of those. Chlorine plus magnesium. Chlorine plus magnesium fluoride. Okay, so we're looking to see, can chlorine replace the other halogen, fluorine? We've got chlorine here, fluorine here. Fluorine is higher in the activity series, so chlorine cannot replace fluorine, so that gives no reaction. And then the last one, we've got calcium bromide plus chlorine. This is going to be a gas. This is aqueous. We're seeing if chlorine can replace bromine. Chlorine is higher than bromine in the series, so this reaction does occur to give calcium chloride plus bromine. And it's balanced as written. That takes us to double replacement reactions, our next type of reaction. In a double replacement reaction, we're going to have a compound reacts with a compound. And that's going to give compound plus compound. So these two compounds produce two new compounds. And the way we would write this is that we have AB plus CD. Okay, compound AB plus compound CD. The pattern is that they're basically going to switch positives and negatives. A from the first compound combines with D from the second, and C from the second compound combines with B of the first. So AB plus CD, A and C change places, B and D change places. You can look at it either way. So as an example of that, we have sodium chloride, NaCl, plus silver nitrate. Okay, if this reaction occurs, think about your metals and nonmetals. The metals basically switch places, so that means sodium here would combine with nitrate, positive 1 for sodium, negative 1 for nitrate, and silver from this compound, Ag, would combine with chlorine from this side. Okay, and again, positive and negative 1, so silver chloride. The equation's balanced. Now, the trick is, how do you know if this actually occurs? Well, in double replacement reactions, we sometimes have a precipitate. That's a term we've used before in lab, where we have a solid forming in a solution. All of these, by the way, this is aqueous, this is aqueous. We could have a gas production. And another possibility is an acid-base neutralization. Or we could, to examine that, we would have to look at pH somehow through an indicator or through a pH meter or something. Okay, we're looking at precipitation reactions first. So if we see a precipitate, or if we can indicate gas production, or if we can show that acids, an acid and a base have neutralized one another, then we can say yes, a reaction has occurred. So the first thing you look for when you have ionic compounds, especially in aqueous solution, is you look at the solubility of the products that would be produced. So you predict what the products are, and then check their solubilities. First of all, with sodium nitrate, the solubility rules, all nitrates, acetates, and ammonium and group 1 salts are soluble. Okay, so all nitrates are soluble. This one's soluble, so we would say that it is AQ, which means soluble. Then we've got silver chlorides. Bullet number 2, all chlorides, bromides, and iodides are soluble, except silver, lead, and mercury 1. So here we've got silver chloride, and that is on our list of chlorides that are not soluble. So this is a solid. What that means is that the silver chloride is a precipitate. And once we find that precipitate, we would say that the reaction does occur, and then we would accept the equation that we've written and make sure it's balanced. It is, and that would be the final answer to the problem. Let's do another. We've got calcium carbonate reacting with hydrochloric acid. Okay, the first indication this is double replacement is that we have a compound reacting with a compound. Okay, we switch ions, so calcium is the positive element, hydrogen is the positive element on this compound, so they're going to switch place. So calcium from here goes with the chlorine of the other compound. Chlorine's a -1, CO3 is a -2, and that also produces H2CO3, hydrogen and carbonate combined, where calcium and chlorine combine. All right. So we look for a gas. Neither one of these is a gas, but we do have a compound that when it forms, when H2CO3 forms, this is, in this case, aqueous. This is carbonic acid. Carbonic acid is somewhat unstable and actually falls apart to produce H2O plus CO2. This is our gas right here. So when we combine all this, we get calcium carbonate. Let's call that solid, plus aqueous HCl. So hydrochloric acid solution produces soluble calcium chloride, plus, instead of H2CO3, replace that with this. It's a separate reaction happening. H2O, liquid, plus CO2, gas. There's our gas production. If we have gas production, or a molecular compound is produced, is another way to put it. But if we have that gas production, then we can say a reaction does occur. Now we may need some balancing here. You can see we've got 2 chlorines and we've got 2 hydrogens there. So if we put a 2 here, we may have it. It's 1 calcium, 1 calcium, 1 carbonate, Well, actually, we're going to have to do carbon and oxygen separately. So 2 hydrogens, 2 hydrogens, 2 chlorines, 2 chlorines, and then we've got 1 carbon, 3 oxygens. We've got 1 plus 2 would be 3 oxygens. So that's a balanced equation. Okay. Another example of a gas production would be ammonium chloride, NH4Cl, reacting with sodium hydroxide. Both of these are soluble compounds. They're both aqueous. Most double replacement reactions, in fact all double replacement reactions, take place in an aqueous environment. This is going to produce ammonium. I'm going to put parentheses around it just to indicate that it's the positive, chloride's the negative, positive, and hydroxide's the negative. So we're going to have ammonium combined with hydroxide, NH4OH, plus sodium going to combine with chlorine, NaCl. All right, this compound has a tendency to break apart into NH4OH yields NH3 plus H2O. This is actually a two-way process, but we're going to focus on the majority of the reaction. So this replaces NH4OH anytime you see it. So that gives us NH4Cl plus NaOH, aqueous and aqueous, yields NH3 plus H2O plus NaCl. So we let this be replaced, NH4OH with NH3 plus H2O. And this is balanced as it's written. Okay, where is our gas? Ammonia is a gas at room temperature, so that would be it, liquid water, and aqueous salt. Okay, and last type of double replacement reaction is the acid-base neutralization. Anytime you see the word acid, you might think this is the possible acid-base neutralization, but it does have to be combined with a base. So acids always contain H+. Bases, as far as our definition that we're going to use here, bases contain hydroxide. So this is our acid, this is our base. Okay. So what we end up with is, if you look at a pattern, we've got an acid, hydrogen with an anion, HA, plus BOH is going to yield HOH, which is water, plus an ionic compound composed of the metal and the nonmetal. So that makes this an ionic. Okay. So starting with a fairly common for a general chemistry lab would be a hydrochloric acid solution mixed with a sodium hydroxide solution. That's going to be HCl. All of our acids are aqueous. Sodium hydroxide, we don't know if this is aqueous at this point or not, but we can go ahead and say that it is, just so that we've got a state there. This is going to give us, let's look at the BA first. From the base, we're going to take the metal, Na, and from the acid, we're going to take the nonmetal. This is a salt. So one of the products of acid with base is a salt. And this is what you normally think of as salt, sodium chloride. And we're also going to produce water. So this is acid plus base yields salt plus water, where the salt is just an ionic compound. Okay. And sometimes in certain sources you would say that if you produce a molecular compound, a new molecular compound such as H2O, that a reaction has happened, but this reaction would occur as written, and it's also already balanced as written. The sodium chloride would be aqueous, and then the water is in the liquid state. Okay, let's do another. We've got sulfuric acid, H2SO4, plus barium hydroxide. Okay, we take the metal from the base, and we combine it with the nonmetal, or the anion from the acid, which is SO4, to make barium sulfate, plus we're going to have water again, H2O. And we're going to need a 2 in front of the water to balance it. This is aqueous, this is aqueous, this is liquid water, and if you go back a few, go back and check, go one more forward to right here and check the solubility rules. One more. There we are. Looking for barium compounds. Hydroxides. Okay, all hydroxides except group 1, strontium, barium, and ammonium, are insoluble. So barium hydroxide is not soluble. So what we would say for that is that we have a solid here. So this is a double replacement reaction, and it is acid-base neutralization, but it also produces a precipitate. So this is an acid-base neutralization with a precipitate at the same time. And it is balanced with a 2 in front of the water. We will stop this, this video at this point. The other types of reactions will be in the next video.